Basically, the integrals along the upper and lower part of our Hankel contour are almost identical. The difference is just the sign of the corresponding regular branch of the pre-exponential function g. To compute the integral along the lower part, we make a standard change of variables, s equals rho e2 minus I pi, where rho changes from plus infinity to 0. And here we go. First, we restore the prefactor e2 minus x plus 1/2, and then the integral itself. The modulus of s is turned into rho under the square root in the denominator of the pre-exponential function. The integral, of course, is a trivial gamma function of 1/2 divided by the square root of x. An identical procedure holds for the upper part of the contour with the same kind of change. There, the pre-exponential function changes the sign, but the integral itself is taken this time from 0 to plus infinity. So double change of sign gives the same answer as for the integral along the lower bank. As a result, we obtain the following asymptotics for our solution for large positive x. Let's immediately fix the normalization constant. We import the condition. For x equals 0, the integral defining the solution simplifies. Let's write it down. To simplify the calculation, let's shift the contour so it coincides with imaginary axis and introduce the variable change, t equals is. Now we need to understand which sign is going to have our pre-exponential function. Well, let's have again one more look on the change of argument when we travel from positive real t to the imaginary axis. Let's choose some particular point x equal to I as naught on the imaginary axis. The change of argument of t minus 1 is pi plus some angle, call it phi, all with minus sign, of course. The change of the argument of t plus 1 is simply the same angle phi. The total change of the argument of the t squared minus 1 is therefore minus pi. After the extraction of the square root, it becomes minus pi by 2. Being put into the denominator, it will give the total I prefactor in the value of our pre-exponential function. So we have. As a result, the integral defining our integration constant is transformed accordingly. Don't forget dt is turned into IDS. The integral is expressed via the so-called Macdonald function, which is a simple modified Bessel function of the imaginary argument. For reference, I'll give you the corresponding formula, but you may treat this integral as just a number. For us, it's enough to know that the integral is approximately equal to 1.98. As a result, we have the following analytic and numeric expression for our integration constant for solution, A1. And here is the answer for the asymptotics of our solution, y1 of x.